Here we have yet another type of series we need to learn, and this is called a p-series. As far as I know, p stands for power. I'm not necessarily sure that's true, but it works for our purposes anyway. So you can see here its general form is 1 over n raised to the p. 1 over n raised to the p. So that could be 1 over n squared, 1 over n to the 1/2, 1 over n, 1 over n to the 7th, anything 1 over n raised to a power. So if you notice, this is really a polynomial more or less. Well, it's close to one anyway. The point is you have a variable raised to a number, whereas with geometric we had earlier, that was exponential. We had a number raised to a variable. So it's going to have this form, and it's another one that's pretty easy to detect. It converges if your power is greater than 1, and diverges if your power is less than or equal to 1. Also going to be greater than 0. You don't want negative powers here. It's not p-series in that case. So again, this is assuming your power is on the bottom of the fraction. So it converges if p is greater than 1, diverges if it's between 0 and 1. So 2 quick and simple examples. All you have to do is look at the power. Well, right here there's an understood 1. Since the power is equal to 1, we look back. Equal to 1 implies that it diverges. That easy. Okay, number 2, we have 1 over n cubed. Since the power is greater than 1, it converges. Now, one way they try to make this a little harder is sometimes instead of actually giving you the equation, they just give you the list, like this. The key to remember here is they had to plug things in a predictable order. So they had to plug in 1, they had to plug in 2, 3, 4. So if you think about this one, it's 1 over 1 plus 1 over 2, and then think how they got from 2 to 4. They squared it. Then how did they get from 3 to 9? They squared it. How did they get from 4 to 16? They squared it. And obviously if you square 1, it's still 1, so that works. So that means this must have originally been 1 over n squared. And since the power is bigger than 1, we would know this converges. So let's look at 2 more like this, where they just give us the list and we have to figure out what the power would be. This is really important. You have to remember this part, that you are plugging things in predictably. So we just have to figure out, okay, what did they do to 1, what did they do to 2, what did they do to 3, and 4, and so on. Okay. So first of all, we have a square root. So let's think about what they've done. They did a square root, and then what did they do to 2 to get it to 8? Well, they cubed it. Okay, then they have a square root. Think about what did they do to 3 to get it to 27? They cubed it. What did they do to 4 to get it to 64? They cubed it. And remember that a square root can be rewritten as to the 1/2. So that means this originally must have been 1 over n to the 3/2. So just to be clear, the 3 is coming from the cubed. The half part is coming from the square root. So n to the 3/2. So you square root it and cube it. And since 3/2 is bigger than 1, it converges. Last example, we have 4 times the square root of 2. Okay, so we've got several things going on here. To change 2 into 4, that would be 2 squared. And then they're doing the square root of 2, which is 2 times the 2 raised to the 1/2. Okay, to get 3 to 9, they squared it, and then the square root of 3 is the same as 3 to the 1/2. To get 4 into 16, they squared it, and then they did 4 raised to the 1/2. Keep in mind, the 4 in particular can be tough, because they could actually have written that as 1 over 32, since the square root of 4 is 2, 2 times 16 is 32. But usually if you just focus on the 2 and the 3, it turns out just fine. So remember, when we multiply things together, we add the exponents. So this will become 2 to the 5/2, 3 to the 5/2, 4 to the 5/2, and so on. So that means our original must have looked like 1 over n raised to the 5/2 from 1 to infinity. And since the power is bigger than 1, this clearly converges.